Last time on Grid World, we left off in a perfect world where our avatar Mario obeyed our every command, and values of states were easy to calculate by multiplying the reward by our discount factor gamma. Then, our avatar discovered something called booze and started making mistakes. Then, the janitor mopped the floor with lubricant, leaving everything slippery. As a result of this madness, we no longer have a perfect grid world. We have entered the twilight zone of stochastic Markov decision processes, and our trusty Bellman equation will no longer work. We must now go where no data scientist has gone before and discover a new mathematical paradigm for handling drunken mistakes and random slips. But what is a Markov decision process, you might ask? We're in a state. We choose an action. And now there are several possible S-prime states we could end up in based on random probability. Does that mean that we have to throw our Bellman equation out, or can we perform surgery and save it? You'll have to wait until the next episode to find out. Just kidding. Thankfully, the solution is quite simple. Each possible state transition from an action has an exact probability, and all the probabilities add up to 1. And remember the Markov property. The probability of future transitions depends only on the present, and the past doesn't matter, baby. Whoa, that's deep. If you master the Markov meditation process, your life can be the same way. And it also helps us save on memory because we don't have to store past states. Alright, so here are the rules for our new grid world. 1. If we tell Mario to walk up or down, he has an 80% chance of obeying, but a 10% chance of going left, and a 10% chance of going right. If we tell Mario to walk left or right, he has an 80% chance of obeying, 10% chance of going up, and 10% chance of going down. If Mario bumps into a wall, he stays in the same square. So all we have to do is loop through every possible state we could transition to after taking a specific action, multiply the value of that state by its probability of occurring, and finally sum them all together. We may be able to save our Bellman equation after all. We'll just chop this out here, add this in here, and presto. Alright, notice all we're doing is replacing the value of S prime for the value of all possible state transitions multiplied by their respective probabilities. So, just a quick note to all the non-mathies to help you understand what's going on here. That fancy Greek E-looking character we just added is called sigma, and it's a summation operator. That means we're going to loop over all the S primes our optimal action could possibly lead us to, look up the value for each state, and multiply it by the probability of ending up there. Then we add them all up. Then, when we're all done, we multiply the sum we got by our discount factor gamma, and finally we add the immediate reward we can expect from our action. So from our starting square, if we tell Mario to go up, there's an 80% chance he'll obey. But there's a 10% chance he'll drunkenly bump into the left wall and stay in the same square, and a 10% chance he'll slip on the floor and end up in the square to the right. This square right here next to the lava pit is our biggest problem. If we try to go up, there's a 10% chance of falling into the pit. Quite a painful death for our agent. Interestingly enough, if our command is move left into the wall, there's an 80% chance of staying in the same square, but a 10% chance of going up near our goal, and a 10% chance of going down away from the danger, and actually a 0% chance of falling into the lava. So that turns out to be the ideal action in that square in most situations. You may be thinking, this is pure madness. How do we calculate our way out of it? How can we know the value of each state? Well, you may be disappointed to find out that I'm not going to tell you quite yet. You see, in order to calculate the value of this square closest to our exit, we need to know the value of this danger square. And to know the value of this danger square, we need to know the value of the square closest to our exit. We find ourselves in a sticky catch-22. And as you can see, this is impossible to solve in just one pass. We're going to need a special tool to dig ourselves out of this conundrum. And that tool is dynamic programming. Dr. Richard Bellman is once again here to rescue us. Want to know how to calculate the correct values for all the squares in this stochastic mess? Well, stick around because you're going to find out in the next unit, which is dynamic programming. And by the way, if you're having any trouble at all or feel confused in this course, here's what you should do. First, go back through the material you've already studied and look for any word or mathematical symbol or term you don't fully understand or feel confused about, and look it up. Second, draw diagrams or write code to help yourself understand the concepts. Don't just read our code. To really be able to apply this in the real world, you need to be able to understand the algorithms and write your own code and follow along and understand what's happening. Number 3, seek out other materials or videos on the subject which may present it in a different light and make things click for you. And fourth, if you're really stuck, don't hesitate to ask for help in our Slack channel. Alright, this is Colin Scout. I look forward to seeing you soon in my next video where we'll take these concepts to the next level. Cheers!